Hello, welcome back again in the Renewable Energy Technology course, and this is lecture series 1.3. Today we are going to discuss about power, flow load curve and head loss estimation. How do you calculate power from hydropower? If you have a river, how much power that river can generate? So, a power that is available in a river can be calculated as QA minus QL times HGR minus HI times efficiency and rho and Z, where PA represents the power available from the river and the QA represents the amount of water available in the river, and QI or QL represents the water that has to be left in the river or the water loss due to spill, flood spill or bypass or some leakages. And the difference in the head between upstream intake and downstream outlet is the gross head, which is represented by GR, and hydraulic loss in the water transport due to friction, bends and the trash racks and all those things are covered by HL or HI, whatever you denote. And then the efficiency in the conversion process is denoted by eta here, and rho is the density of water. So, first of all, before calculating the power, we need to understand the flow duration curve. Especially this is important to know when you are designing a run-of-river schemes and you are planning to connect that to the grid. So, if you go and measure the flow in the river, it will not be same throughout the year. So, in the rainy seasons the flow will be high and in the dry season the flow will be low. So, depending upon that, the flow can vary over the year. And the flow duration curve shows the percentage of time which a particular flow rate is likely to exceed in any given year. We have an example in this curve here. So, if you look at this curve and the table, so you can see that Q10 is 1.069 and Q95 is 0.067. What does this mean? The meaning of this is for the 10% of the time we have the flow in the river that is 1.069 meter cube per second, but for the 95% of the time the available flow that you can guarantee is only 0.067. So, there is a huge difference in the flow. So, this curve is basically representing how much flow is available for a particular time of the year for the particular percentage of the time. And if you look at here, the mean flow in the river is 0.474. Now, in river you have to reserve some flow for some environmental reasons. So, reserve flow is the minimum flow required to avoid aquatic life damage in the water stream, and this is normally 10% of the flow. And the farm flow is the flow being available X percentage of the time, where X is the percentage specified by the users, and it is usually 95%. And so, while you can design the powerhouse taking the mean flow as the design flow, and sometimes people design the powerhouse at Q40 or 60, that means at 40% exceedance or 60% exceedance. So, you need to calculate how much is the power and how much it means in terms of economic analysis. So, here you can see the lowest line is the minimum flow here, and this is the highest flow available in a year, and this is the mean flow. And as I said earlier, you can design at the mean flow, or normally the practice is to design at Q40 or Q60. And also some places have 2 times rainy season. So, in that case you might have a different power curve. So, if you look at this is one of the examples that I have chosen from a place where you have 2 times rainfall. So, one is in the time of November, December, and another in the time of April, May, and this is what the power output looks like at a different flow. And the project has been designed at the 0.7 meter cube per second with a net head of 207 meter. Now, if you are not going to sell the power in the grid, and if you are designing a powerhouse for supplying the local areas, in that case we must assure that the power is available most of the time to supply or to meet the demands. So, in that case we cannot make a power plant to run at the partial load, I mean with a Q40 or Q60, because we will have more power, but at the same time that is not available throughout the year. So, some of the months we cannot supply the powers. So, that is not an efficient and wise design. So, what we design, how we design is we choose the flow at 80 to 95%, so that I will go again. So, flow duration curve specifically for the off grid. So, we have seen that if you are selling the power to the grid, then in that case going with the Q40 or Q60 makes sense. But if you are designing a powerhouse which will be going to run in the isolated mode without connecting to the grid, then that powerhouse must meet the minimum demand that is in the village. So, we cannot design at Q60 or Q40 from the economic reason. So, powerhouse will, in that case will be designed at least 85 to 95% or 95% exceedance, and which will be very much low power in that sense. So, either we have to increase the head and meet the demand. So, we do not have options to choose the flow. Flow is determined by the river, but we can always try to meet the demand in the locality by trying to vary the head if available in the vicinity. Now, once you have understand about the flow, the design flow, and how to estimate the flow, now I will talk about head losses. And there are various head losses that has to be accounted while calculating the net head, and the head losses comprises of frictional losses in the pipe, which is the main component within the head loss, and also there is some frictional losses in the trash rack or the screen, and also when you are passing the from different sections, there are some sudden contraction and expansion losses in the pipe, and also if there are some bends, horizontal and vertical bends in the pipes, that also contributes some head loss. So, basically the summation of head losses are the summation of frictional loss, losses in the trash rack, losses in the contraction expansion, and also losses in the bends. And the friction loss in the pipe can be calculated by using Darcy-Weisbach equation. And basically the head loss HF can be calculated by multiplying F times L by D times B square by 2Z, where HF is the head loss, F is the frictional factor, L is the length of the pipe, and D is the inner diameter of the pipe, and V is the velocity of the fluid, and G is the acceleration due to gravity. And again, this frictional factor can be calculated using Colebrook-White equation, and then the equation is as follows. And during the calculation of this frictional factor, you will acquainted with this internal roughness of the pipe, another coefficient, and this coefficient E is depends upon the surface and what type of the materials that have used for the pipe. And F is the friction factor again, E is the internal roughness of the pipe, and D is the diameter of the pipe work. And this is the formula with the for the Reynolds number more than 4,000. And the friction loss in the pipe, you can also calculate using the Modi diagram, or calculate using the standard roughness coefficient available for different surfaces. And here are some list of the materials and the index roughness coefficients. So I'll go to the next kind of losses, frictional losses, that's on the trash rack. So a screen is nearby, always required in the entrance to stop the debris or other things entering inside the water inlet. So however, when you have some obstruction in the water path, it will have some losses. So that loss that due to trash rack is given by KT times T divided by B to the power 4/3 times B square by 2G into sine theta. And where H is the head loss, T is the bar of the thickness, and B is the width of the bars, width between the bars, and V is the approach velocity at what water is coming, and G is the gravitational constant, and theta is the angle of rotation from the horizontal that the trash rack is inclined at. So, and if you look at this the factor K, and you can get depending upon the width, and the K factors could be various factors that you can choose from the graph again, and then use here to calculate the head loss due to trash rack. Now another loss is the contraction and the expansion loss. This happens when you have a change in the sectional cross-sectional area within the pipe. So if the pipe is, if you have two different sizes of pipe within across the alignment, then at that time you have this kind of contraction and expansion losses, which is again represented by SC is equal to KC times V square by 2G, where KC is substituted by KX EX if you want to calculate the losses during the expansion. And you have here the value of K, and the value of K, that is this constant, depends upon the ratio of D by D, that is the diameter of the two different sections. And based upon the D by D ratio, you have different K values for certain contraction and for certain expansion, and you can choose the value of K and put this in equation, and you can calculate how much head is lost during contraction or during expansion. Another type of head loss in the penstock pipe is at the bends. So whenever you have a bends, there is a change in the direction of a flow, which creates some turbulence, and that will create some head loss. And the value of, again, this head loss in the bend is given by Kb, which is a constant, times B square by 2G. The value of Kb depends upon the total length of the bend, which is also proportionate to the angle alpha, shown in the figure here, and it also depends upon the radius of curvature, ratio of radius of curvature of the bend and the pipe diameter D. The radius of curvature R is usually taken as a radius of curvature of the central line of the bend. So what does that mean? So if you try to bend, put a bend of, let's say there is a bend of 60, degree, then you cannot put one bend of 60 degree. You can put it, but there will be high head loss. So it will be recommended to break down the bends into three sections at least, so that you have greater this radius in the bend and less loss due to this bend provision. And again, you can get the value of kV from this curve here and use in this formula to get how much is the head loss due to bend. So once you have calculated, once you know how much is the flow available, how much is the net head available in the project, then you can easily calculate the available power using again the formula that I have shown earlier. Now I would like to give some tips before ending this session. How do you survey the site for hydropower? Because this is very important in designing a hydropower, that you have a good survey, and survey has various aspects need to be considered during the site survey. So you have technical aspects. During the technical aspects, you need to understand how to select the site itself, and when you are going to select the site, the first thing that you have to keep in mind is we try to minimize the length of the headdress and penstock so that we can build an economic project. Now at the same time, we should also careful about the stability of the site, and also if the local materials are available or not. Maybe you have a good site, but the local materials are not readily available, and it might need to a lot of transportations. And also while choosing the components location, like for the location for forebay, location for gravel trap, or location for descending basin, we should be very much sure that if we'll definitely put the spillway in these structures, so this location has to handle this spill water, and there should be some colci or some small tributes or the river itself nearby, so that we can flush back this sediment or this sand to the river safely. Also, we should think of flow measurement, and hydrology is important parameters during the site survey. And during the flow measurement, at least there should be few spot measurements of the flow, and it is preferable to measure in the dry season, so that you know what is the driest flow available in the river. And also to prepare the hydrology is important, and for that you can also have take some nearby gauging stations data, and estimating a good flow is always important in the powerhouse design. Also, site geology is important to figure out, and what kind of soil is available, and how is the soil structures, how depth your structure need to go, what kind of soils are there, also depends upon that. And some soils are not good for the structures, and that need to be tested with the site geology. And also one more thing that you need to consider is the water test. That is, how is the water, how much sediment is there in the water, what is the water pH value, all these things need to be considered, and these values also determine the sizing of the, for example, the sediment concentration available in the water determines the sizing of your descending basins, and the water quality determines if whether or not you have to have anti-corrosive paint inside the penstock or not, or if there is too acidic water, then you need to have anti-corrosive paints especially required in the different components in the hydropower. So these are the very important technical aspects that you need to consider. And also when you discuss about the social aspects, there is the issue of land use. Are those components that you are planning to have are the land of government, or is it public land, or it's a private land. If it is a private land, then what is the land use? Have you got the permission from those landowners? If not, what is the process? So these things need to be considered. And also there is a water right issues. So you have, in most of the cases, you have to register the river for the projects so that you get the permission to use that water resources for your project. And also, if you are designing an off-grid system, then what are the possible end uses in the nearby vicinity, and what is the household demand? So based on this household demand and possible end use demand, you need to determine the size of the projects. And as I said earlier, you cannot vary the flow, because you have to choose the flow depending upon the flow available in this river. However, there is some possibility to vary the head. So in that case, you might need to have some options so that with that available flow, you can meet the demand of the village with increasing some head. And also, it's always better to have to design multi-purpose project, or if there is already existing canal, irrigation canals or canals is already available there, then such infrastructure could be used for the power generations. Then in that case, the project might be much more economic. So these aspects has to be think of when designing, while doing the survey, and this also impacts your design. And also, while designing, you should also consider about environmental impact on the air quality during the construction of the projects. If you are constructing a larger size project, you should also think of displacement issues. I hope this will be dealt in more details by in the next lecture. And also, impact on the biodiversity, impact on aquatic life are the important parameters that need to be considered during the survey of hydropower. I hope you enjoyed the presentations, and I have been able to give some of the overview of small and micro hydro in this course. Thank you very much for listening to me.